Okay, so today we're going to talk about topic 2, which is electrical and electromechanical systems. Our objectives. Now, you've taken circuits before. Hopefully, you recognize some of these terms. Create the mathematical models of circuits using Kirchhoff's voltage and current laws. We may talk about voltage divider, loop analysis, and then there's an ethics part of this topic as well. Now, down here in the table, I just want to kind of give you a taste of where we're going, because we're not just going to stop at electrical. We are going to continue on. We start with mechanical. That's a really important one. Electrical is pretty important for us. But we're also going to cover a little bit of hydraulic and thermal and how they relate. But everything has some kind of input. If you think about like a through variable, this is what's kind of causing the change. And you have the across variable. So for example, for a mechanical system, I have a force causing some kind of change in motion. Same thing here, we may have a current that's giving us a change in voltage, and those can be flipped as well. But we have our three elements. So whereas a mechanical has a mass spring damper, in a circuit, we also have two elements that can store energy, the capacitor and the inductor. And then energy dissipation, is the resistor. That's going to take energy out of the system. So there are some relationships here, and we'll see that some of the equations also match up well as well. First off, some things use electricity. Are you aware of that? Okay, good. We're going to talk down the road. We've already talked about solenoids, but now we can actually loop the circuit part into it. Actuators. Do you have any examples? Do you know any examples of like solenoids or actuators? Still thinking. All right. Do you have doors in your car that do you have to crank them closed or like locked, or do you use a key, or you sometimes just hit a button? Hit a button. Okay. So those are solenoids right there. You hit the button. It's gonna tell the car to power the solenoid. The solenoid is going to move position, then it's going to lock the door. So that's a pretty quick example. But obviously, robots around here, they have different actuators. It's used in HVAC as well. Anything to kind of open, shut, that's typically a solenoid. So our elements we're going to talk about, there's passive elements. These cannot introduce energy into a system. So these include resistors, capacitors, inductors. Now, they can store energy, some of them, but they will not introduce energy. So that's a passive element. And then we also have active elements. These do introduce energy into a system, such as a voltage or a current source. Okay. So we're going to go through all those different elements. We're going to talk about some of the equations that are on the equation sheet, which you may be a little bit familiar with, and then we're going to do some Bo-Body today as well. So let's start with the basic. This is our first passive element. This is called the resistor. This is on the equation sheet in the box. This is Ohm's law. This is for an ideal linear resistor. We talked a little bit about how we're treating some of these elements. We're saying that they don't change over time. Do resistors change their resistance in different environments or as time goes on? What do you think? You put it in a cold environment compared to a hot environment, it does change a little bit. But in this case, we're just treating it as one steady R value. So voltage, and you might hate this, but the textbook, when it's talking about voltage, it uses E to represent voltage. So the voltage of the resistor is equal to R times I. If you don't like this, you can use V. That's fine. I'll probably switch back and forth depending on what the problem. Sometimes the problems ask for a voltage V, but this is what the book uses. What does a resistor do? Resists the flow of current. Yes. So as current flows through, it's going to try to slow it down. And from that, it's going to create a voltage drop. And so they convert it into heat. And basically, they're taking energy out of the system. Hey, we're looking like a class now. It's good. Welcome. We're transitioning from mechanical to our next favorite topic, electrical. What element takes energy out of the system from the mechanical? What dissipates heat? Maybe changes it to heat. Turns energy into heat. Friction. Great. So this is very similar to a damper in that it takes energy out of the system. And so, again, this is Ohm's law. We've got our voltage drop, which is equal to R times I. We're not going to worry about power in this class. We don't really have the time to get there. But the main thing is, anytime I see a resistor, I know I have this relationship. Whatever that current is going across it, multiplied by R is the voltage, which can help with our Kirchhoff's voltage law. Question. This was an easy one. The other two maybe haven't seen as much, and that's where we can really rely on the equation sheet anytime we see one of those other elements. So let's go to the next one. Capacitor. Okay. So a capacitor looks like this. Basically what it is, it's two conductors separated by some sort of insulator. So do you know what it does? You kind of know? So yeah, basically it can accumulate charge and it can kind of stop it until there's enough charge to bridge that gap. And honestly, this is used for a lot of different stuff. Like my pool pump at home, there's a huge capacitor because I'm putting 220 volts into it. But the capacitor is there to protect the motor. And so what it does, it doesn't allow you to just flip it on and the motor starts turning because that's going to burn out the motor really fast. So the capacitor allows, once you flip the switch, charge builds up on the positive side, and then it slowly starts to come over until we get up to speed. So that's what every motor starter basically has, a capacitor to make sure we're not just giving full power right away. Protects a lot of downstream elements. Now, this one, this is analogous. Well, first off, it can store energy. So even after I shut the switch off, there's still some charge there, so we still have some energy. This is similar to like a mass. A mass can store energy. Capacitor, these are both types of capacitances. Okay, let me put a C here. Now, on the equation sheet, I don't usually use the Q dot, but usually I'm looking at the current of the capacitor. I sub C is equal to C E sub C dot. So let's talk about how we get here. Q is charge. So as you know, I have a voltage here, charge is building up. C is the capacitance, and then obviously we've talked about E. Any kind of E in this class is a voltage. If you don't like it, use V for volts, that's fine. Now the time rate of charge, so how the charge is changing, we can say is Q dot, that's equal to the current, which is just I. And so if charge is equal to C capacitance times voltage, if I take the derivative, C doesn't change, but the voltage does change over time. You don't have to understand this, okay? We don't necessarily use these ones down here, but this equation right here is what we're going to use anytime I have a capacitor. Basically, the current is related to how the voltage is changing over time. The voltage drop across those two conductors, plates. And so we can set up a relationship. Basically, we're looking at voltage as the output for any kind of capacitor problem. AC output. That's our voltage. So a resistor doesn't give us an order to the equation, but this does have a first order derivative. So anytime I have a capacitor, I'm going to have a first order equation for that capacitor. And, you know, as we build circuits with different number of elements, that can just kind of add up, you know. And so we'll talk about that as we do bow body. How many equations should I look for? In this case, for one capacitor, it's one first order equation. Okay. Everyone okay? Welcome to circuits. Yeah. The last one is the inductor. And again, you don't really have to understand much of what's going on here. This is just the background information. I'm going to get to the equations soon. But if you know anything about inductor, it's a coil of wire. And so they also store energy. When current flows through that coil, it creates a magnetic field. So even when you shut the system off, there's still energy stored there. And so it can still go for a little bit of time. So we have something lambda, which is equal to L, which is the inductance of whatever that inductor is, times the current. The lambda is the magnetic flux. Now, we can relate the magnetic flux to voltage. So voltage across the inductor is equal to lambda dot, the change in that magnetic flux. So my equation here, and I'll have it right here, we have this relationship where the voltage of the inductor, that voltage drop, is equal to L, the inductance, times IL dot, how the current is changing with respect to time. So basically, inductors and capacitors work oppositely. If you look at their equations, they look very similar. They're just switched. So in this case, current is the output. It's a first order derivative. So therefore, it's going to be a first order equation. Anytime I have a inductor, don't worry about the energy and power. We don't really get into that, but we will use this quite a bit. I'm going to use that equation anytime I have a capacitor, and that's on the equation sheet. So we can always relate voltage to current for all of these: resistor, inductor, capacitor. Questions? Okay. You might think, what is this analogous to? Because it can store energy. So capacitor is kind of like a mass. There's a way that we can store energy. Inductor is kind of like a spring. So I can store energy just like a spring can store energy, just a slightly different equation, right? So there are some relationships. We'll talk about that a little bit more, but ultimately, just knowing how to plug these equations in. KVL, KCL. No questions? Everyone good? You all had solid circuit classes, I'm sure. Is that true? Okay, good. So there's two different sources. These are the active elements. And so we've got a voltage source that gives me a set voltage. Then we've got a current source that gives me a set current. Over here in the room, actually, we have these are both. So you can either set the voltage or you can set the current. So a lot of power sources you can kind of choose. When we're doing our problems, if I'm given a current source, I don't know what the voltage is. So I can't also set up equations where I have E in. I don't know what that voltage is. Same thing for voltage. If I have a voltage source, I don't know what the input current is. I just know what the input voltage is. So you just got to be careful when you're setting up your problems. You only have one input. I can't have both an E in and an I in. Okay. And then it does show you direction. Typically, we draw our circuits like this, where current is flowing up and then to the right. That's what you'll see. Questions? Okay. So here's some of the analogies again. You don't have to understand it perfectly, but basically, there's usually some kind of input and some kind of output. And then we have our three different elements. So we've got two ways to store energy. Then we have our energy dissipation. So what's going to happen is that these equations can look very similar to some of our mechanical ones because they have similarities. Now, the only thing that's really changing is the letters. So I'm using R now instead of B for damper. I'm using inductor L instead of K, spring. All right, so there's a lot of similarities. There's a lot more stuff online. In fact, I think I got this. I used to show some videos that were not the most upbeat, and it's hard to pay attention to. But there are people on the internet that, if you'd like to explore more about analogous circuits, you can search it on YouTube. So some people on there, again, it's a little bit hard to follow, but you can draw a circuit that gives you the same mathematical model as a mass spring damper. So this circuit does the same thing as that. The equations look identical. Why would you do that? I'm not really sure. Back in the day when they didn't have simulation tools, this was one way that you could kind of test things out. Hey, if I change the resistance here, how does that change my output? We can then kind of take that to the mass spring damper. Now we've got our simulation tools like SimScape and all that, where we don't really have to do it. But that is something that, if you're interested in, you can definitely look up online. Okay? So put that on your list of things you want to do after you graduate, right? Yeah? I'm sure you'll check it out. All right, electrical systems. Okay, so we have our three equations, which are on the equation sheet. Now we're getting closer to what's our goal here? How do we use body? So for electrical systems, the important dynamic variables are voltage and current. And like we just saw with our capacitor and inductor, these are related to the energy storage. So depends on capacitor voltage, depends on inductor current. The mathematical models of the electrical system should be written in terms of capacitor voltage and inductor current. So basically, and this is the last one, which I think is pretty important, the voltages and currents that are not one of those, because the way that they store energy, inductor stores it in the current, capacitor stores it in the voltage. Anything that's not those two, such as the voltage drop across a resistor, E sub R. I don't want the capacitor current. I don't want the inductor voltage. I don't want basically anything. I don't want any other random current, anything like that. Basically, I want to use my voltage law and my current law to try to put everything in these terms, as well as my input. So I have some kind of input, En or In, I've got these as my outputs. And all of these other ones, we can try to substitute something in here. So I don't have these at the end. That's the goal of our circuit equation. So we'll do some problems today, and we'll keep doing them for the next couple of days, just to see how we can separate this out. Questions? No? Okay, do you remember Kirchhoff's voltage law? Okay, let's all say it on the count of three. 1, 2, 3. Didn't work. Okay, the voltage law. There's a lot of words here, but basically, for a loop, a closed loop, it's got to be a closed loop, and you could have 4 or 5 loops within a circuit, right? So you just have to define some kind of closed loop where I can always get to back to my starting point. Let's say we start here and go clockwise. So anytime I'm going from a positive to a negative for the terminal, that's going to be a drop. So that's a negative voltage 1, negative voltage 2, negative voltage 3, and then that's a positive because that's my input. The other way that we can write this is E in, so I can just rearrange it, is equal to E1 plus E2 plus E3. Basically, the input voltage is equal to all of the drops in voltage. So gains equals drops. And sometimes our loops, they don't have a voltage source connected to it. So one thing I really want to do is make sure you label the terminals so that, if I'm going from positive to negative, that's a drop. Or if I'm going to negative to positive, that is a gain. So you want to make that clear in your circuit so you don't get too confused. Okay, so that is KVL. And then the other one is the circuit current law. So what is the current law? Okay, yeah, so all currents entering has to equal all the currents leaving, right? And that's at a node. So voltage law is about a loop, a closed loop. This one is just at a node. And so, yeah, we've got all of the sum of all the currents entering and leaving has to be equal to 0 because there's no energy storage here. So in this case, we've got 2 inputs, I1, I4. So we could write it like that. We could also say we have I1 plus I4. Those are entering. And then these ones are leaving. So the sum of all entering has to equal the sum of all leaving. Okay. So those are the laws that we have. Anytime I have a node where current splits, I want to make sure I write this as part of my definitions. For mechanical, we've got Newton's laws, right? Circuits, we have Kirchhoff's laws. So we want to make sure we write all of these down in my definitions before I start trying to put it all together. All right? Okay. So we've got all the tools, we've got all the definitions. Now we're going to talk about how to actually model these. In bow body, this is where we get to the definitions part. Basically, we're going to write the first order differential equation for each energy storage element, capacitor or inductor. So these are our equations right here. We're also going to write down KVL and KCL as our definitions. And then from there, now this gets more to the diminished. Then we can take those and try to fit them into each other, make some substitutions, and be able to get to a final mathematical model. And again, all of our differential equations should be solely in these terms. You know, if I have a capacitor, I should have an EC. If I have an inductor, I should have current for it. If we have a input voltage or input current, that's obviously got to be somewhere within the mathematical model. And then sometimes my equation might have an output voltage that we care about. So if there is an output voltage, that's obviously going to be our output. And so we can change our equation to be in terms of E out. I already talked about it a few slides ago, but I don't want any resistor voltage in my final equation. That should be able to be changed to be in terms of these. Okay, so there is a proper way to format it. And once I get to my final mathematical model, then we can see if we can make a transfer function. So if it is a pretty simple circuit, we can create a transfer function. If not, sometimes we just have to leave it as is. Okay. And this is full body. We start with the same thing. We're going to breathe. Now, for the circuit, the order, and again, you don't have to be perfect at this. We're just trying to identify mostly number of equations. So the number of first order equations is equal to the number of capacitors plus inductors. So for example, if I have one capacitor, I have one first order equation. If I have two inductors, I have two first order equations. If I have 5 capacitors and 2 inductors, what am I looking for? 7 first order equations. You won't see a problem with that. Too many. Now, some of these you can, take multiple mathematical models and then you can put them in terms of each other and solve them there. But at this stage, we're just going to look for, depending on capacitors and inductors, how many first order equations we have. You're going to draw the circuit, identify inputs, outputs. This is where we're going to put our KVL, KCL equation sheet definitions. Then we're going to try to diminish it. And if it's possible, we're going to create a transfer function. If I have single input, single output, we can make that happen. Shall we try a problem? Example 3.1. We want to derive the mathematical model. Okay. So, just like with mechanical, sometimes, well, this is our first time doing a circuit, and some of you really hate circuits. I understand. I'm a mechanical as well. But I ended up having to do a lot of circuits at my job, and I didn't remember anything from college. The only thing I remembered from my circuits course was the guy said if it's not working, unplug it, wait a second, and then plug it back in. That's what I remember from my circuits class. Not much. But you may have stuff, especially if you get into R&D, sometimes you got to do the circuit side. So we're going to start slow. We're still going to just follow the steps because some of us really don't like circuits. And so as long as I can kind of lay it out, put everything down that I do know, hopefully we can piece it together from there. So this is an easy example. We're going to build up from here. The first step is to breathe. This is not the last course you have to deal with circuits. You still have 480 after this. So it's important stuff. Now we have the order of the system. What would the order of the system be? One, I have one inductor, therefore I'm going to have one first order equation. And because it's an inductor, I'm going to have an IL dot. The way that it stores energy is through the current. And so I'm looking for one equation with an IL dot. Resistor doesn't add to the order. The active element doesn't add to the order. It's just if we have a capacitor or inductor. Okay. No questions? Everyone's okay? Body diagram. Now, with this one, with circuits, I'm okay. Like homework, tests, if you just want to draw on the circuit. I understand you're not really drawing much different. Free body diagrams, that's where we do want to isolate the bodies, change, springs to forces and stuff. But for this one, the only thing that I would add, because I have most of it here, is we already have the current. Current is really important. So some problems they give you the current, sometimes they don't. So it's typically we're always going, up and to the right. It's like a nice clockwise motion. But what I do want to have is the terminals. So how should the terminals be on here for the inductor? Should it be positive, negative, or negative, positive? What do you think? It should be positive and then negative for both of them because they are going to be voltage drops. So they're they're stepping down the voltage. They are not introducing voltage. The only time I have negative to positive is if I have an active element, something that's putting energy into the system. So otherwise, we're good. We've got our current. It's just a single loop. So everything is the same current. That's good. I even like they denoted it by I sub L. So that is my inductor current. That's what they're saying. Now this is the same current that goes not only through the inductor, but through the resistor and the voltage source. So that current is all the same. It's all equal. Okay. All right. Now identifying inputs and outputs. What is the input? Thank you. EN. The voltage. Yeah. Anytime I've got a circuit, that's the input. That's what's giving it energy. If I don't have that, nothing's happening. Now, the tricky one is going to be output. We've kind of talked about it a little bit. But this is dependent on if it's a capacitor and inductor. Because I could either look at current or voltage for those. So for the inductor, what is our output? It is IL. Because the equation is the voltage is equal to L IL dot. Therefore, this is the output. This is what's changing over time. If I had a capacitor connected here, I would have two outputs. I would have the current of the inductor. I would have the voltage of the capacitor, EC, as well. So they have different outputs. They have different ways of storing energy. And so just, again, it's all based on the equation sheet. What has the dot, that's what's changing. That's my dynamic variable. That's my output. Now, some problems will ask you for a certain transfer function. Well, in that case, they're going to specify what the output should be. And so sometimes I can change capacitor voltage to be related to inductor current. And so that's also something you can look out for as well. Okay, so we've got inputs, outputs, and here we go. We're going to do our definitions. Now, has anyone used impedance? Anyone take Rodriguez? You took Rodriguez? You took Rodriguez? Some of you took Rodriguez? So at this stage right here, the defining diminishing transfer function, I'm going to teach you two options. So today we're just going to focus on this using the equation sheet, some of those examples I had, some of those equations, how to put it all together and solve. if you're familiar with impedance of like, hey, I really understand voltages and currents and how to look at a system and try to identify like a transfer function, that's another option. So we can still follow Bobati up to this point, and then here we might deviate. So next class, I'm going to teach the other option, okay? But today I'm just going to stick to some of this, and you get to choose which makes more sense to you. So if you understood what was in Rodriguez's class, great. You can use that method. If you didn't feel very confident on it, there's this method. Both of them get you to the same transfer function. It's just different ways to look at it, okay? So I kind of threw this in a little bit earlier after a couple of years realizing some people had different circuits knowledge, and so trying to accommodate for that. So let's go. Definitions. Let's do our definitions. So I have my equation sheet, which is pretty helpful for circuits. We can do some definitions. For example, one of them is going to be my resistor voltage. So I do have a resistor. Resistor voltage is equal to R times current. So that's one definition. Now I want to be specific because what is the current going through there? Yeah, so let's change that to R times I sub L. Because all of them have the same current going on. My inductor, I get this equation from the equation sheet. Voltage is equal to L IL dot. So I have my definition. I still need a little bit more, but our goal is to get one first order equation relating this current to the input voltage. So I need something with the input voltage. What else are we missing? En is equal to what? En is equal to E out? I wish. I don't actually see an E out here. That would be a nice equation. En is equal to, thank you. So the last thing I need is kind of like my Newton's second law. I need some kind of relationship for all these, my sum of forces. In this case, my sum of voltages. So my voltage law, KVL, is, I can start here, then I can go around the loop. Again, we've got our terminals like that. So we have a positive En, we have a negative El, we have a negative Er, and that gets us back to 0. Or we could say that En, the input voltage, is equal to inductor voltage plus resistor voltage. So now I have an equation with a relationship for my input voltage. We're almost there. Questions up to this point? Do we need a KCL? Why not? Yeah, there's just one current. It doesn't split anywhere. So we don't have any nodes where it splits. Therefore, nothing like that. So for our diminished, you know what? I guess I keep it all on one slide. So this is defining the variables. Now I'm going to use that KVL, and we're going to plug in our definitions. So this equals L IL dot. This equals R IL. And you know what? That's my equation. Because we already said it's a one first order equation. Input is En, output is IL. And so we've got one first order equation just like that. So it's helpful, especially if designing a circuit, if I want to know how long it takes for this to reach steady state, which we'll talk about after test one. But we can plug in different R values, different L values to see how that affects what's going on in there. Maybe if I increase my voltage, what happens there? Yeah. Well, what that means, because I know that this is resistor voltage, but I'm not keeping that term in my final answer. So I'm just keeping the R times my dynamic current. So in that case, I don't have it defined as just ER. That's what I don't want in the final answer. But anything, like obviously I'm going to have to use it to expand out. The last thing is creating the transfer function. So we can put this in the S domain. And that allows us to combine dot becomes S. So the dot becomes S, then we can combine all like terms. So we have LS plus R. And now we can get our transfer function where output current over input voltage is equal to 1 over LS plus R. We have a first order transfer function relating voltage to current. Okay. Now again, this is one way to do it. We're still going to follow body. When it comes to the transfer function, there is a second option we'll talk about next class called impedance, where you can look at the circuit a little bit differently to be able to solve for it. Okay. Wow, we're doing really good on time. You're feeling okay? Somewhat? Okay. Let's see what's next. This one's called Your Turn, but it's example 3.4 from the textbook. Anyone use the textbook while they were doing their homework? Yeah. There's no full body. Why bother? I want you to find the transfer function relating output to input. Now this one's got two loops, so it's a little bit different, a little bit more complicated, but it's all the same rules. So I'm going to give you some time to try to think through it, and then obviously I'll kind of do some of the parts going forward. But you can work with the person next to you trying to solve some of these things. We can solve this. What's the order of this? Yes, we're looking for one first order equation or one first order transfer function, just like the last one. Will be as e. Then you can draw your diagram, terminals on. And so it's first order, we have one capacitor. What is I know the input, right? It's IN. That's what's causing the system to change. I need that energy input. But what is the output? It is going to be E sub C, the capacitor voltage, because our equation is IC, the current is equal to C, DC dot. So therefore, EC is our output. Yep, that's what we want our transfer function. So we got input output, we've got our diagram. Now we diagram definition. And again, something that's going to help you is just using the equation sheet. We got a lot of stuff here. So does anyone use the equation sheet all the way to That's okay. Yeah, like most of the mechanical stuff. It's not. But once we start going into some of the lower down equation sheet, that's where it gets hard to memorize. So trying to. So at least you can put down some of those definitions. Yeah, ACL. Sorry. I definitely have a current law. Should have a voltage law. 2 voltage laws? 1 voltage law? 3. I don't know. I'll bring it up next time. Okay, definitions. I have my capacitor. I'm going to put that down. I have resistor 1. Its current is I sub C. And I have resistor 2, which current is I2. So we've got our elements. They all each have an equation that's going to be helpful for us. Hey, look at that. Got a KVL, KCL? KCL, he's working on KVL. You got some definitions going. Hey. Hey, that's what I got. Oh, you got an extra one. A little bit extra. Okay. It splits. The current does split. So we can do a KCL at node A. Now, some people have asked me before, like, does it matter where we take it from? Because technically, there's also a point at the bottom of this. Well, it doesn't matter. Because either I take it here or I take it down here, it's the same relationship. I've got 2 coming out of 1 or 2 coming back into 1. So at KCLA, I have IN coming in. That's my input. And then leaving it, I have I sub C and I2. So that's pretty good. I've got those definitions. Are we good? We need anything else? We got the split. Shall we move on to the next step? Does anyone have any questions? Okay. Because if I move on, we cannot come back. If we can't come back, wait, no, we can come back. What's the other law? KVL. Okay. Now, technically, I have 2 loops here. KVL 1. So I labeled them. Here's my loops. Some people put like arrows, and that's confusing to me because that usually to me means a current. So I just like to label it like this. Here's my loop 1. Here's my loop 2. Now, KVL 1, like I know this has a voltage, this has a voltage. Do I know the voltage of the input? It's not 0 volts, right? Not, because I'm setting the current source. So this is not applicable because we have IN. And we don't know the actual input voltage. It's not 0, but it could be changing a little bit. We're just setting the current. So I actually cannot do a KVL for loop 1 Anytime I have a current source, that's impossible. I'm not going to make up an EN, okay? That doesn't work that way. Can we do it for 2, though? Is it a closed loop? It's a closed loop. So if I go around 2, let's say I go clockwise. We like to think clockwise. So if I start at A and then I go clockwise, that's going to be a drop, negative ER2. If I continue around the loop, then I'm actually going up negative to positive across the capacitor. So that's actually a gain. So that would be EC. Same thing for ER1. And this gets me back to where I started. So the sum of all the loops on that, the sum of all the voltages on that closed loop has to equal 0. So we can move ER2 to the other side to look like that. Now, if you don't really, that's kind of hard to understand. Here's another way to think about it. The current is always going to split to have an equal voltage. Like the total voltage across here, which is EC plus ER1, because they add in series, that total voltage is the same voltage across R2. So current has to always split to give you equal voltage. So that's another way you can kind of set up your KVL relationship right there. Questions? Everyone's having a great time. Okay. Let's go on to the next slide. So, you know what? Before we do that, in my inputs and outputs, I identify what my inputs and outputs are, like what my final transfer function should be. I have a lot of stuff going on. I've got this, I've got this, I've got this, I have this, and now I have this. That's 5 different things. We're going to use all 5 of them. Okay? Sometimes for different problems, we might use things more than once. We got to use all of them. So I've got 5 total things. Where would you like to start? And I personally like to look at my inputs and outputs. I know that EC is an output. I know that IN is an input. I know that EC is an output. So some of these things I can identify like, hey, I like that. I like this, and I like this. So just trying to figure out what's going to stay. Everything else is going to have to be substituted out or, moved around to get the transfer function we want. So based on this, what would you like to start with on the next slide? Maybe it's a toss-up. Like, this might be kind of hard to do, but maybe here and here. I would probably, since I know this is my input, maybe I'm just going to do this. Now, either one works. It's not like one's going to give you a different answer. But let's just start here. And then we're eventually going to use all of the 4 other ones to plug in. Okay? So, next slide, KCL is our starting point. KCL. So we have IN is equal to IC plus I2. I like IN. I'm not going to change it. That's my input for my transfer function. We're not touching that. The other 2 I do not like. What would you say we should change I sub C? Do we have anything from our definitions that we could replace it with as a variable that we like? Yeah. Cool. So C dot, that is the definition for the capacitor. Current is related to voltage with the first order derivative. And now I like that because that's my output. That's great. But the other current I don't like. So what would you replace I2 with? What has an I2 in there? This is why we follow body, is because we can kind of look back and say it again. ER2. So I2 is equal to ER2 over R2. The voltage of the resistor over the resistance gives me my current. So now at this point, I like IN, I like EC, that's my output. I do not like ER2. So we go back to our definitions. What's something that I can replace ER2 with? We could do that, yes, because that is a definition of ER2. And what that would do is that would get me back to I2. And this is where it gets a little bit circular, because sometimes, yeah, if you use the same definition, we're just going to go back in circles. And so then we go, okay, let's work back. Now we're back here. What's another thing I can plug in for ER2? Because that didn't work. Very good. So EC plus ER1. And now we're a little bit closer. I like this. I like this. I don't have to change that. But the only thing that I don't like is I don't like the ER1. So let's rewrite it. I like this, but I want to replace ER1, and ER1 we can replace with, again, I look back at my definitions. I have a definition for ER1. R1 IC, because it has the current, same current as the capacitor. So that gets us really close. R1 over R2. I just want to change that IC, and that's the same thing we did back here. That was the first thing we changed. When I had that capacitor current, I changed it to the C EC dot. So now I have all of them, all of my outputs in terms of capacitor voltage. My input is still the current, and that looks pretty good. All right, so now it comes to formatting. So we have all the outputs we like. We have the input. Formatting, we want to, just like with the mechanical, I want to have all of my terms on the same side. They're already on the same side, but I want to group up all the like terms. So I have two of the derivatives here. I want to combine those. So this becomes C times 1 plus R1 over R2 times the derivative plus 1 over R2 EC. And this, I'm getting closer to a transfer function. I don't want to see fractions within fractions. So if I was to create a transfer function with this, I'm going to get these fractions in my denominator. I don't like that. What's a way that we could get rid of all these fractions right here? Yeah, or multiply it both by R2. So if we do R2 over here, and we take all of this and multiply it by R2, then I get R2 times the current equals, this is R1 plus R2 d C dot plus E sub C. So just by multiplying both sides by R2, that takes out all those different derivatives, or sorry, those fractions. It just makes it look a lot cleaner. And now we have a good first order equation. Now what I'd like you to do, before we take a break, we got to finish this out. I want you to create the transfer function. So take that, dots become S. We can get our transfer function, then after that we'll take a break. Dots become S. So we have an R2 in the numerator, but this is our first order transfer function. Now, one thing that's really important, especially when you have a transfer function that relates the whole thing together, I should see every single element in there. So we have an R1, R2, and C. All three of those are in there. So it's another way you can check it. Like, I can't just have one just kind of floating around not doing it. They should all be present in the transfer function because they all play a role. If I change one of these elements, it's going to change how the system operates. Okay. We're going to take a break, then I'll do a quick other example. We'll talk about offense, and then yeah, let's take a break. So it's 8:13 right now. Let's come back at 8:18. We'll do a few more example problems. And if you have questions, I know that was 49 as well. Yeah. Yeah, yeah. Yeah. I know. Some year they'll make it. Okay. Welcome back. More people are coming. Ow, here. Oh, that stabbed me. Okay, we're gonna do a harder problem, but you're not gonna have to do it. I'll do it. And you can kind of pay attention. We're gonna try this problem where we're trying to determine the transfer function of the current inductor with respect to the input voltage. So I have some different loops, and we'll see how it goes. So for this, the first step is breathe. You can do this. Oliver, what would you say the order of the system is, or either of you? Yes, I have an inductor, so that's going to be one first order equation. I'm going to have an IL dot. I have one capacitor, therefore that's also another first order equation with its output. And so therefore in total it is second order. Now, the question, if I go back here, it actually wants me to find a transfer function of the inductor current with respect to the input voltage. This is probably going to be a second order transfer function. So we're going to have to do some rearranging, substituting to get there. Because in total, this is a second order system. Okay. So now we're going to get to the body diagrams. Wish I made this larger. Okay. I can put my terminals in. These are all going to be voltage drops for all of them. What else am I missing that's pretty important? I need the currents, right? So what happens is that at this node, the current splits. So I'm going to get this current, I'm going to get this current, and then at the end here, they come back together. So there's going to be a current all throughout there. So in total, I've got 3 different currents, and I can call them whatever they want, whatever I want, whatever you want. What do you want to call this current right here? I1, okay. What about this current right here? IL makes sense to me because that's what it's going through. So that's going to help me with my definitions. And then this last one, C. Makes sense. And some people call them like I Jeremiah or something like that. It's up to you. It's just a lot of writing. So the simpler it is, better. But I need to have that denoted. There's differences here, and so then we can solve using those subscripts in our equation. Okay, so I think this is a good body diagram. I got all the currents. I've got all of the plus minus. That should help me when I set up all my definitions. Any questions up to this point? Okay. Inputs, outputs. I know that my input is the in. That's no problem. Voltage is what's causing the system to giving it energy. What are the outputs? Very good. These are really my 2 outputs. I have capacitor, which has a voltage. Then I have an inductor, which has a current. That's how they store energy. You include both of those. Now, the question did ask for one of those particular for my transfer function, so I can also use that to kind of help me out. Now we go to our definitions. Now, first off, I'll do the easy ones first. So I call this I1. This is IL, IC. So the Ohm's law for ER1 is equal to R1 times I1. The voltage for R2 is equal to R2 times IL. The inductor voltage is equal to L IL dot. And then the capacitor current is equal to C EC dot. Great. So those, again, that all comes from my equation sheet. I don't have to memorize it. I just know anytime I have inductor, I'm writing this equation down. Anytime I've got a capacitor, I write this down. That relates current to voltage. These are going to be in my final equations because I should look for 2 first-order equations, and then we can try to get to a transfer function. How am I doing? Have I done it good so far? Am I doing okay? Okay, now it gets to the tricky part. We got to use some KVL, KCL. What would you like to do first? You want the KCL first? Okay, KCL. So I'm looking here or here, doesn't matter. But my total current, I see, that goes into the node. And it splits into these two. So we've got I1 and we have IL. I'll look at the other side, just the same relationship there. We have two currents combining to become one. Okay, now I've got two loops. So let's look at the first loop, KVL1. Oops, KVL2. KVL1, I can start here, I can start anywhere, but I'm going to have a positive EN, and then all the rest should be negative. So positive EN, everything else is negative. Those are all drops. That should get me back to where I started, equal to 0. So we could say that EN is equal to ER2 plus EL plus EC. Now KVL2, I don't have an input, but we talked about this before. The current's always going to split to give me equal voltage. Now I could just start at this node and I go clockwise. So from positive to negative, that's a drop. So we have negative ER1. And I continue going around clockwise. And now for L, I'm actually going from negative to positive for both of them. So that's plus EL plus ER2. This gets me back to where I started, equal to 0. So what we could say is that ER1 is equal to EL plus ER2. Current splitting to give me equal voltage across there. So now I've got 7 different equations. And some of the things that I like this, I like this, I like this, I like this, 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 and the other one I don't actually like any of them. But it's just trying to identify, what are the variables that I'm okay with. In this case, KVL2 doesn't even have any that I like. I don't want any of these in my final equation. So I'm not going to start with this one, I don't think. I'd probably start with KVL1 is a good idea because it's got 2 of them. I could start with KCL. It's kind of up to what we think. But we have options. It doesn't matter where you start. We should end up at the same potential final answer, final transfer. Any preferences? KVL1? Great. So the next slide, I'm going to start with KVL1. Now, what I'm looking for here is because I have both a capacitor and an inductor, I'm looking for 2 first-order equations. I'm looking for one with an IL dot, and I'm looking for one with an EC dot. And then from there, we can combine it to get our final transfer function that the problem asked for. Okay. So let's take KVL1. We have EN is equal to ER2 plus EL plus EC. ER2, if I look at my definitions, for Ohm's law, this can change to R2 times the current, IL. The inductor voltage we can change to L IL dot. and we're going to keep EC. Now, let's take an inventory of these variables. I like EN, I like IL, I like IL dot, I like EC. So we're actually done with this equation. The only thing I'd want to do is rearrange this. I'm okay. Look, this is an output variable, this is an output variable. But in this case, this equation, the output is IL, the inductor current. Everything else is going to go on the other side. So we can just say that EN minus EC, capacitor voltage, is equal to LIL dot plus R2 IL. That's a good first equation. I don't have any other derivatives. It is just my one output variable, IL. And so really the difference in these two voltages is going to dictate what that current is like going between on that leg. So this is a good way to format it. It's just trying to keep all the output variables together, highest order first. Then we've got this. I can't make a transfer function out of this because I have a difference there. So it's like two inputs giving me the current. Questions? Nothing? Okay. Now, we still have a lot of equations to use. I used 3 of them. I used KVL1. I used the 2 definitions right there. But there's still a lot left. I haven't used this. I haven't used that. I haven't used this or that one. So we've got a lot left to use. I'll probably start with the KCL just because I like that right there, and then we'll see kind of where it goes. Cool? KCL? KCL. Let's, we have I sub C is equal to I1 plus IL. And we can change the capacitor current that's equal to CEC dot. And I1, what would you like to change I1 become? You got anything with I1? I don't like I1. I want to get rid of it. So if I go back here, I only have one I1. It's right here. So I can say I1 is equal to the voltage ER1 over R1. Plus, I like this. Okay, so let's take inventory. I like this. I like this. I don't like ER1. So what can we change ER1? Now, I know this can be a little bit hard, but the nice thing is that we are constrained to these definitions. Like I've got these definitions, I've got these definitions. Some of them I've already used. Now again, sometimes you can use them twice, but I need to use at least everyone once. So I'm going to use them. Yeah. Yeah, so I can use this. I can substitute it right now to get that. Very good. So we got C EC dot is equal to 1 over R1. This is where we're going to use our KVL2. ER1 is equal to ER2 plus EL. plus I. Okay, now we're actually back at a point. If you look here, right, we had an ER2 plus EL up there, where we could just make the same substitution, right? Because we had a definition for ER2, we had a definition for EL, and it's good, maybe. Although, what happens if we, so we have CEC dot equals 1 over R1 times R2IL plus LIL dot plus IL. So I can do the same thing that I did for the first equation, and I get a second equation that looks like this. This is not good. I'll tell you why it's not good. I don't want to have two different output variables going on. I don't want to have two output variables going on. So can't have multiple output variables. What that means is I can only have one variable with a dot in each equation. I want to try to avoid this, because this, I mean, I've already got IL dot. So the equation we want should just have an EC dot. Got my IL dot here. This one I'm trying to get an EC dot only. No combination of the two derivatives. The variable can be there as long as I don't have two different derivatives. So I got to go back to the drawing board. This doesn't work just doing the same substitution I did the first time, because that gives me a different derivative. So I'm going to try to figure out another way to change this. What else could we use to substitute this out? Do we have an ER2 plus EL somewhere else in our definitions? Let's go back. Okay. First off, I can't just substitute this back, because this is what we used to get here. We used KVL2, so I'm not going to substitute and just make it equal to ER1. But I have KVL1 here. KVL1 has an ER2 plus an EL. So what I can do is say that this is equal to EN minus EC. So I can use KVL1 again to be able to change this. So by using KVL1, we can say this is equal to EN minus EC. And that actually gets me to a place where I've got all my variables are good. Okay. This takes practice, trying to find, what's going to give you an equation, what's going to give you a final ordinary differential equation with just one derivative. I've got to have just one in each one using this method. Now, if you like to use impedance method, we'll talk about it next class, where you can kind of bypass some of that, so it can be a little bit faster if you know what you're doing. But I've got my one equation. Now I've got my other equation. I'm going to move this over to the other side. So we have C EC dot plus 1 over R1 EC is equal to 1 over R1 En plus IL. And we can simplify this a little bit by multiplying everything by R1. So now I have two first order equations, one with an EC dot, one with an IL dot. Got a lot quieter in here. I just want you to know, like, this can be a little bit going in circles sometimes. Of I try this, I put it in. I just want to encourage you. The last slide with all of my definitions, that's what we're constrained to. I know those are set, those are good. So if something doesn't work, I got to maybe back up a little bit, like here. Oh, that didn't work. So let me figure out something else I can substitute. And this way, now we have two different separate first order equations. Okay. So looking at this, I can't create a transfer function with just this. I can't create a transfer function with just this because they both have essentially two inputs, but the whole circuit is related. Like the currents are related to the voltages. There is a relationship going on there. And so the problem did ask actually for a specific transfer function. That's what we're going to look at next. Obviously, I'm out of room here, but are there any questions? Anything that didn't make sense? Yeah. Yeah, so that would be like having an IL dot and an EC dot in the same equation. Now, you can have the variables, but I can't have two separate derivatives all within that one equation. Yeah. That's something we want to avoid, even for mechanical and stuff. I want to make sure, if I've got theta dots and then x dots, that they're in separate equations, not together. Until we get maybe to that transfer function, we can substitute one of these. But at least for this process, we want to keep them separate right now. This one, you know what? I'm not sure. I honestly don't know. I can't erase it. I'm not sure what's going on there, but that's not a dot. How about that? That's weird. Okay. But yeah, that's just an IL, and so therefore, okay, that didn't work. So now we try something else. Yeah. All right. So we're gonna go to the next slide. We're gonna create a transfer function as the problem specified. We wanted. They're looking for a transfer function of IL with respect to En. So can we actually model this to figure out what that current is with respect to the input voltage? Now, the first thing that I would do, because we're getting into a transfer function, is I want to change all the dots to S's. I want to get it into the S domain. So we have En minus EC is equal to LS plus R2 times IL. So we can do the same thing for both of them. We change the dots to S's. And I like to capitalize it just to show we're now in the S domain. Wait, I messed up somewhere. It should be R1. Okay. So if I want to get to a transfer function, again, the impedance method is a way to get to the transfer function as well. It's a way to kind of look at it in terms of a certain variable. But from this, we want to get to that transfer function where we have IL and EN. What are we trying to get rid of? What do we not care about? We have two outputs, but they already chose one of them. So what's the other one that we're going to get rid of? EC. I don't care about EC. So what I'm going to do is I'm going to take one of these equations, I'm going to solve for EC, and then I'm going to plug it into the other equation. And that's how we can go about this. Now, which one is easier? I'm not really sure. I'm going to, is this right? My equations right? Yeah, they're right. Okay. Let's just choose one and plug it into the other one. So I'm going to choose this one. EC is equal to En minus Ls plus R2 times the current. We're going to take this definition, we're going to plug it in here. So this is how we can get rid of it. I'm going to rearrange this. I'm going to solve for EC. Now we're going to plug it into the other equation, and this will get us closer to that transfer function. So now we have R1 CS plus 1 times En minus Ls plus R2 times IL. And this is equal to En plus R1 IL. Okay. Well, how do we want to do this? I can get all my ENs to the same side. So we have R1 CS plus 1 En minus En. So I get all my ENs to the same side. And then I've got on my right hand side, I have an R1 IL. And then I'm going to add this all over. So this is R1 CS plus 1 times LS plus R2. So that's added to the right hand side because it was negative on the left hand side. And we're almost there. So with all this, there's a good amount of algebra. However, Laplace transform does make it nice because we're able to group all that stuff together. We're able to make this substitution. For example, this En, I have a 1 En minus En, so that cancels out. This right here becomes R1 LCS squared plus R1 R2C plus L times S, and this becomes R2. So that's just FOILed from what's going on here. So I've got all that multiplied there. And then finally, I just have an R1 CS En equals R1 LCS squared plus R1 R2C plus L plus R1 plus R2. that is our going on. Now I might have lost you somewhere in here with the substitutions, and that, like, obviously I have some experience with this, so it's pretty. And my dad was an algebra teacher, so here we are. But we're creating the substitution, making sure that we do each step at a time. I don't try to solve it all in one step. That's why Bobati, I'm just trying to do each part that I can. But our goal was to get rid of EC. We just cared about IL over EN. That's what the problem asked for. So by using the Laplace transform, the substitution, we can actually get rid of it. And now my transfer function, IL over EN, is equal to, this is where we can just put it all together in the transfer function form. So it's not anything different. It's what we got here. There's our transfer function. So we can see all of the components are there. Capacitors there, inductors there, all the resistors are there. So by changing one of these components, we can change how the circuit's going to respond in that system. Okay. These take practice, especially if you don't have much circuit knowledge, but all of them are based on voltage law, current law, and then in this case, taking a more complicated two equations and combining into one equation. So that's where the algebra comes in. Yeah, it does take some paper for sure, but giving yourself some space so you can solve it. It's really easy to make mistakes on the algebra side. Questions? Because I have one last short topic that we'll cover more next class as well. But no question? Looks complicated? You'll be able to do these soon. We started easy. Obviously, there's some tougher ones. The homework, it's not like you start out, this is a baseline. There's easier ones than this, so you'll get a little bit of experience as you go through the homework. I want to do one last subject, and then we will get out probably a little bit early. We'll continue this topic next time in class as we talk about impedance method, but op amps, operational amplifiers. Remember working with these in instrumentation? You remember? Remember how we'd always just take them out of the circuit because they never really worked? We would just do the gain in LabVIEW. Anyways, op amp, what it should do is put some gain on the signal. Like it's going to take an input, it's going to put gain on it. And it's not just for gain, it's also using filters. So trying to filter out different things. The way that there's a lot of different configurations, if you remember from instrumentation, I can filter out. I can do a low pass filter, a high pass filter. I can do a differential. There's lots of things you can do with these op amps to increase the signal that's coming out of it and all that. And this is the inverting terminal, negative terminal. This is the positive or non-inverting. Now, we have some really simple rules with these. We are not building these in this class, okay? We're not using real ones. We're in the ideal world of like how it should work, not actually dealing with 471. But we've got some easy stuff. So it'll simplify some of our whole body. You don't have to write this down, but we're not going to use this. Output voltage is equal to K. So, if I put some kind of resistors around here, I can build some kind of K, some gain. That's related to the difference in voltage right there. So we can look at different types of gain for that. But these are the three properties. These are listed on the equation sheet. So you don't necessarily have to write them out. But when we're dealing with an op-amp, we're going to do an example real soon. The first thing is that we're saying there's no current going in here. No current. It's drawing negligible current. So basically the current is bypassing the op-amp. The second thing is that the voltage difference we're also going to say is equal to 0. So if one of these is grounded, typically positive is grounded, that means that the voltage at this part is 0. So that's a way we can simplify what's going on. There's no current and there's no difference in voltage. The last one we don't care too much about, but that we're going to say the gain is infinite. And so from these definitions, we can simplify our whole body that the voltage is equal and there's no current going to the op-amp. Again, you might remember some of your experience with op-amps, but if we had like an inverting op-amp, what that does is it takes the signal and it's going to invert it, so it's going to flip it and it's going to put gain on it. And so the problem is if you have too much gain, you can distort your signal. So trying to find that right balance of, what resistors we should use to give us the right gain that we need. Okay, so I know you've got some op-amp experience. Hasn't been great probably in the real life. We're just dealing with an ideal op-amp. These are the three laws. Really, we just care about these two. There's no current and there's no voltage difference. From there, we can solve for the output voltage. Like what's my output voltage as a function of the input voltage? That's typically what we're looking at, input output. Okay. Ready? Maybe? Oh boy. We're doing this one? Okay, we're doing this one. It's not the worst. Example 3.6 from the textbook. We have an op-amp circuit. We have an input voltage and we have an output voltage. We want to derive the relationship between input and output voltages. What this means, anytime I've got a op-amp, our goal is to find the transfer function of E out over E in. That's our goal. So if any circuit has an output voltage, we're always looking at that output voltage with respect to the input. In this case, it's a voltage input. Okay, so this is our first time with a op-amp. It looks different. It looks a little bit scary. We're going to start with the breathing. Take a breath. Okay, wait. We have some rules. We're just going to try to follow the rules and hopefully we can get to a final answer. Any guesses about the order of the system? Oh, by the way, the op-amp doesn't change the order. So what would the order of the system be? First order, great guess. Let's see, how many capacitors we have? How many inductors do we have? None. So there's no order. 0th order, which means no derivatives. That's what it means. We don't have any derivatives. So our final answer, our transfer function, actually is going to be no s's. No dots means no s's. in the transfer function. Now you might recognize this configuration, maybe not. It might be a little bit different than what you've seen before. So we'll see how it goes. But our transfer function, no s's, it's just going to be a nice constant value is what we're going to find. Okay, now we get to the diagram. And the only thing I would add on here is our terminals. So what's happening, it actually shows you where the currents are going. So this is like an output voltage. This is like something that you can plug in another device, or maybe this is going out to LabVIEW or something like that. But this is going to be a drop. So the output voltage is a voltage drop because something else could be taking that energy when you plug it in. And so this is our circuit diagram right here. We've got our terminals, currents, everything like that. And by the way, this current is just going to stay like this. This is all going to be one current right here. We'll talk about that as we do our definitions. Okay. Inputs, outputs. Wait, questions? Inputs, outputs. This one's pretty easy. My input is E in, and my output is E out. And that's really what it is for any op-amp problem. We always have some kind of input. We're looking at the output. How does it change? We can figure out what that transfer function is. And then our definitions. And then we'll be done once we get that transfer function. First off, if I have an op-amp, I'm going to start with the first two. The current going into the op-amp is equal to 0. It's negligible. So the op-amp has two rules. First one is that there's no current going into it. That means that this current is nothing. That's very helpful to us. The second part tells us that the difference, EA minus EB, equals 0. So the voltage difference at the two terminals should be 0. They should be the same voltage. Now, what is that voltage? Do we know either of these voltages? Do we know the voltage of EB? You know, Braden? All right, let's follow the lines. EB is connected to ground. So EB is equal to 0. So if EB is equal to 0, then EA has to be equal to EB, which is equal to 0 volts. So the two op-amp laws are extremely important because what they tell us is that this voltage, if this voltage is 0, then all of this voltage is 0, which means the volts right here is equal to 0. That can be a little bit hard to understand, but we know that these two voltages have to be equal to 0, or they have to be equal. So therefore, they're both 0, and there's no current going through here, which means the same current here is the same current here. So that's another thing, that I1 is just equal to I2. So these two currents are equal, and there's no voltage here. Okay, question. Let's see. We've got a couple other things we can do. Um, mm, let's start with, this is kind of solves our KCL. We don't really have a KCL now because those two currents are just equal. It just completely bypasses going to the op amp. So I1 is equal to I2. For this loop and this loop, we do want to set up some kind of KVL. Now, I would call these partial KVLs. This looks incredibly complicated. I don't think I'm going to go all around the loop because then I have to go through the op amp. Same thing with this. It's kind of complicated. But because of our op amp rules, I know that this point right here is 0 volts, voltage equals 0. And I know that once it gets to that node on top, the voltage is equal to 0. So for KVL1, I can say I have a positive E in. Then I go across ER1, that's a drop, and that gets me back to 0. So therefore, we can just say that En is equal to ER1. Because I'm going from 0 volts, because these are equal. So that's one relationship. Then we have this relationship. I start at 0 volts and I end at 0 volts because this is all connected to ground. And so for KVL2, I start at 0. I have a drop, ER2. I have another drop, E out. That gets me back to 0. So therefore, ER2 is inversely related to E out. ER2 is equal to negative E out. So I have all the equations that I need. I mean, this kind of fed into the KVLs, this part right here. That's what I used to kind of solve these KVLs. We knew that the current is 0, so therefore the currents are fine, so I don't really need a KCL. So this kind of frees up a lot. I'm really just going to use these two equations to be able to solve for my transfer function. Then we'll be done. And I will post this video, so hopefully that's helpful if you're going through it. We're going to do more op amps next time in class, so we'll get a little bit more extra practice. But those two laws are extremely important. It simplifies it. I can kind of forget about what's going on here and just look at partial voltage laws from 0 to 0 volts. No questions? Like, let's get out of here. Okay, so when I'm looking at this, I like E in, I like E out. So I can use either of these equations. I'm just going to start with E in. E in is equal to ER1. So if I start with my KVL1, E in is equal to ER1. Now I have my definitions. So based on the, oh, you know what? I totally forgot to write that down. ER1 is equal to R1 times I. There's all the same currents. I can just write it as I. ER2 is equal to R2 times that same current. So we can just use the same current for all of them. So I can say En is equal to ER1, which is equal to R1 times I. We can rewrite I. I is the same thing as ER2 over R2. Because they share the same current. This is equal to 0. And then we have our relationship from KVL2, where this is equal to E out over R2. So we can rewrite this as negative R1 over R2 times E out. Okay, so to get E in, to get to my transfer function, E out over E in, we divide both sides by E in, we divide both sides by that, we get negative R2 over R1. That is our transfer function. That is 0th order. I don't have any S's. This is an inverting amplifier. So we've worked with it in mechanical instrumentation where, hey, if I set R2 and R1, I can get this relationship. Now it is going to flip the signal, but it's going to give me gain. So I can figure out what that gain is based on that ratio. Okay. All right. So that's how we can solve it using those op-amp laws. We're going to look into this more next time in class. So next time we're going to talk about impedance. That's another method where you can kind of solve this to get to a transfer function. That's an option. If you don't know anything about that, I would recommend just doing what we've done. But I'm going to teach it as a second option. We're going to look a little bit more at op-amps next time in class, and then I'll pass out some. You'll have some other group problems next time in class as well. But if anything didn't make sense from this, stick around. I can go back to it. You'll get some practice on the homework in the next 2 weeks too. Cool? Questions? All right. You can stick around or leave. It's up to you.